Hello and welcome everybody. Greetings to our new webinar for this week. So the webinar this week is the design of complex measurement systems and their challenges. So we are going to talk about basic settings and stuff that is necessary for all kind of measurements and especially for complex measurements. At the beginning, I would just like to talk about some organizational stuff for you so you can easily command your system and your software. To allow also other peoples to log in. So just for you, on your right side of your corner, you have the possibility to ask questions in the chat. Those questions are anonymous and nobody will see them. It's just me and my colleague. And also on your right side of your chat, there are handouts that can be downloaded during the webinar. If the handouts, if you did not download them, just write us an email and we will send them afterwards to you. That's so far from the organizational stuff. Just some two sentences about the person sitting in front of the camera. So the speakers today is going to be Verena Niederkofler. She's application engineer and technical know-how expert for today. Say hello, Verena.
Hi.
Do you want to say something about yourself?
You pretty much introduced me already. So my name is Verena Niederkofler and I'm an application engineer for DEWETRON for a little bit over a year now. And I'm going to do the second part of the presentation for you today.
Perfect. And myself, I'm going to be the moderator today. So I'm Ivica Paresic. I'm business developer at DEWETRON and sales for Austria. So that's about us. Just some short information also about DEWETRON for those who don't know DEWETRON. DEWETRON has 120 employees and its headquarters is in Austria, in Graz. We have 3 subsidiaries in worldwide, so it's Germany, USA, and China, and we're active actually in more than 25 countries, and we have more than 25,000 systems and 400,000 channels in the market, which is making us a know-how expert and expert in measurement systems. Our portfolio, just a short information, our mobile measurement and rec measurement solutions. And part of those are, of course, our power analyzers, which we are known for. And to make this package round and complete for our customers and partners, we offer the necessary service and calibration for our products worldwide, of course. So at the very beginning of this webinar, I would like to start with an example of a complex measurement system so you can see what our systems are capable and what complex measurements are. And then my colleague Verena is going to take over and talk about different sensors, multiple measurement locations and synchronization stuff, and basics regarding measurements. So let's talk about the complex measurement application and what the application is. So a complex measurement would be, for example, if you talk about this example, the visualization of gas formation in flowing liquids. And the complexity within this project is that you can't use active sensor within the liquid. So based on the principle of a CT, we use an X-ray that has to be deflected and also detected by 1024 detectors with 5 megasamples per second each to achieve a high quality result at the end of the measurement. So just once more to make this, to help you realize it, 1024 sensors at the same time has to be recorded synchronously with up to 5 megasamples per second. So if you think your measurement application is complex, just think about this complexity of 1024 sensors at the same time with 5 megasamples. So what was the DEWETRON solution for this application? We had 8 separated systems which are automatically synchronized with each other, equipped with a multiple amounts of measurement modules. In this case, it was the Trion 3 multi-module. And we use the function generator from DEWETRON to control the X-ray beam as well. And each system was streaming over a 10 gig Ethernet to the analysis PC where those pictures have been generated. So that's just from my part from now, just a short explanation of a complex measurement. Verena is going to take over. Just again, the hint, use this webinar. If you have any questions to the things that Verena is going to explain and show you, ask those questions in the chat window. Nobody can see it, only me and Verena, and we are going to answer those questions at the end of the webinar. So Verena, the stage is yours.
Thank you very much. Okay, so let's start with the next topic, the use of different sensors. So for many applications, different sensors are needed, and those different sensors should be supported by the hardware and by the measurement system to avoid unnecessary expansion of the system. So I would just like to talk about some important parameters or some considerations which are important for some sensors I chose, which you can see on the side. So what needs to be considered? First of all, the supply of the sensors is very important. On one hand, for the sensor to work correctly, and on the other hand, for example, for zero flux sensors, the supply of the sensor, or rather a redundant supply of the sensor, is a crucial aspect. If the measurement system for some reason doesn't have a supply anymore, then the sensors are supplied redundantly to avoid any damage of the sensors. For IEP sensors, so acceleration sensors, also the excitation current is very important. These sensors are based on a piezoelectric effect where a force causes a displacement of the charges and a voltage can be measured, as you can see in the picture below. The excitation current is also used for the internal electronics, which consumes up to about 1 milliampere. And typical excitation currents for those sensors are 4 or 8 milliampere. This is especially important if long cables are used, since there is an inverse relationship between voltage and capacitance, which can be seen as the cable capacitance here. So the current has to be high enough in order to drive the signal along the cable and to avoid an attenuation or distortion of the signal, and in order to get the right and significant results. For temperature sensors, I chose 2 different ones, the thermocouples and resistance temperature detectors. Thermocouples are based on the principle of different material parameters, which are included in the thermoelectric coefficient, which is seen as K in this formula here. And based on those different material properties, the temperature can be measured or calculated. These sensors are cheaper than the RTD sensors. They have a high temperature range, which goes up to 1,800 degrees Celsius. They are not as accurate as the resistance temperatures, though. The resistant temperature detectors, they are based on the principle that the resistance changes with temperature, and usually there's a linear relationship which is used for the measurement. These detectors or the sensors are more accurate. They are also more expensive, and they go up to about 600 or even some up to 800 degrees Celsius. The next sensor I would like to mention are strain gauges, which are used to measure stresses and strains in different bridge circuits to determine delta R. So different bridge circuits are used, and the more resistances are applied on the sensor, the higher is the accuracy. For example, for half and full bridges, the transverse and the longitudinal elongation can be measured. it is really important to consider that there are different wiring types for those bridge circuits, for example, to compensate lead and temperature resistances. So it is important to consider this whenever you have to use or you want to use strain gauges for your application, that the hardware and the measurement system supports this wiring type which you would like to use. The last sensor I would like to talk about are the encoder sensors. These are used to determine rotational speed, absolute angle, and the turning direction. So therefore, they have usually three inputs, A, B, and Z, whereas the A and B input have a 90-degree phase shift in order to determine the turning direction, and the Z signal outputs an impulse per revolution to have the absolute angle precision for each revolution. For those encoder sensors, it is very important to consider that the hardware has a high enough bandwidth and input frequency in order to resolve the pulses per revolution, which are output by the encoder. The pulses per revolution also have an impact on the angle resolution, as you can see in this example here. For example, if you have a pulses per revolution or an encoder which outputs 360 versus 1800 pulses per revolution, you get an angle resolution of 1 or 0.2 degrees. Those encoders also have different modes. So they are all based on the same principle that if input A leads input B, the counter increases, and if input B leads input A, the counter decreases. Depending on if the rising or the falling edge of input A and B are counted, they output or they count the different amount of pulses. So for example, for the mode X1, the counter increases on the rising edge of A and decreases on the falling edge of input A. For the mode X2, the counter increases on the rising and falling edge of A and decreases also on the rising and falling edge of A. So here it's just important which input leads the other. For X2, the rising and falling edge of input A and B are counted. And here it also is important if input A leads input B or input B leads input A. So if you know or if you want to use a special mode, you should also make sure that the hardware supports this mode you would like to use. So then we come to the next topic, the multiple measurement locations with great distances. Therefore, the synchronization and the remote control are very important to consider. But why do we even need synchronization? I would like to explain it with a small example. So if you have system A, which has a timing error of 39 ppm, and system B has a timing error of 15 ppm, and both systems start recording at the same time, you get a timing error between the systems of about 62 seconds, so 1 minute between both systems after a month of recording. Of course, this could be done in the post-processing by manually synchronizing the data, but this means a lot of effort, a lot of work, and not every time realistic, since both timing errors of the systems have to be known beforehand. But this can be solved with synchronization very easily. So if system A is sync master and system B is synced to system A, system B also has a timing error of 39 ppm. Both systems and the data of both systems are synchronous to each other, independent of the recording time. So this timing error can be neglected and you don't have to worry about it anymore. So there are different possibilities of synchronization, which also depends on where the measurement systems are located, which accuracy is needed. Yeah, so for an integrated possibility, I would like to mention our own integrated synchronization source, which is the try and sync bus. This is always included in our DEWETRON systems. It has a relative time synchronization, an accuracy of 60 nanoseconds plus minus 5 nanoseconds per meter, and is limited to 100 meters. It is a very easy synchronization possibility. Another synchronization possibility is PTP, the Precision Time Protocol, according to the standard. It has an accuracy of 100 nanoseconds and is also limited to 100 meters via a LAN cable, but also greater distances are possible with PTP-capable switches. The two next possibilities I would like to mention is IRIG. So IRIG is limited to 50 meters. But it can also be reached up to 300 meters with special cables and special switches. It has an accuracy of 2 microseconds, and IRIG is based, or there are different IRIG signals. Here I mentioned IRIG A and B, that there's also other signals, and it refers to the pulses per second which are output. And then there's an AC or a DC signal, so you can have, for example, an IRIG B AC signal, which you would see in the second picture below. And in the first picture above, you see an IRIG B DC signal. So the AC signal has a sine wave as carrier signal, and the DC has a DC signal, of course. So here you can see a reference pulse, a 1 and a 0 as an IRIG signal. The reference pulse has a length of 80% of the pulse length, because IRIG is a pulse width coded signal. The second pulse is a 1, which has a length of 50% of the pulse length, and a 0 has a length of 20% of the pulse length. Another important consideration might be the phase mismatch between the channels. There's no delay in theory, but in practice you can find a delay in the nanosecond range, which is neglectable for sample rates in the kilohertz range. But if that might be a consideration or something important you have to consider for your application, this should be kept in mind. So for the remote control, I would like to focus on the remote control itself, and not so much on the data transfer, which is of course also possible with different interfaces. But if I talk about the remote control today, I refer to, for example, to different commands like start and stopping the recording, loading or saving a setup, or set a data file name. This is especially important if the systems are at different locations or not easily reachable, or if someone doesn't want to go to the lab just to start a recording, but wants to sit in the office, for example. So one possibility is the RDP, the Remote Desktop Protocol of Windows, and the VNC, which enables the access to the system. It's very easy to use. The screen content is transferred to a local PC. You can sit in front of your office PC, and it's like you sit in front of the measurement system, because you also have access to the keyboard and mouse. Another possibility is SCPI, so Skippy, also called Skippy. This is a plain text interface via Ethernet. Communication layer is TCP/IP. There is a broad spectrum of commands available, like start, stop the recording, saving or loading the setup. You can set a data file name and also have access to channel properties. Data stream is a binary interface via Ethernet, also with the communication layer of TCP/IP, and the configuration is done via Skippy, so the same commands are available. The next two remote control interfaces are XCP and EtherCAT. XCP is another binary interface. Communication layer can be chosen to be TCP/IP or UDP. It is possible to use with Canopy or Inca, and with our software. And here you can start and stop the recording. Of course, data transfer is another topic then. The probably most complicated or complex interface is EtherCAT, since another or more additional hardware is required to use it. And here you can start and stop the recording and also load a setup. So you can, for example, prepare different setups in advance, since you cannot change the channel properties here. But if you load, or if you use to prepare different setup in advance, you can load different setups with different channel properties afterwards, so you don't have to go to the measurement system. Okay, so let's come to the last part of the presentation, which is the consideration of different parameters, which I would like to mention real quickly. So we have the sample rate as the first parameter, which has to be considered, of course. So the sample rate must be at least twice as high as the highest frequency of the signal, as it is known for the Nyquist theorem, which has to be fulfilled. So usually the sample rate is chosen to be 10 times as high. Okay, so to demonstrate this, I prepared something in our measurement software Oxygen, which you should now be able to see here. So with the signal generator, I have here a sine wave with 5 kilohertz and 10 volts. And I sampled this signal with the frequency generator, or I have the sine wave comes from the frequency generator, and I sampled this sine wave with 200 kilohertz, which you can see here above. And then I sampled the sine wave also with 10 kilohertz, which is the double def maximum frequency, and 50 kilohertz, which is 10 times the maximum frequency. And here below in this picture or in this recorder, you can see the difference. So if we just look at the original signal and the 10 kilohertz sample signal, you can see, if we zoom in a little bit, that the signal gets sampled twice per period, and you can reconstruct the signal, but it looks more like it looks like a triangle wave, and doesn't really have to do anything with our original sine wave. If we sample it with 10 times the highest frequency, you can already see, I don't know if you can see a lot of difference on the screen, I hope so, that you can reconstruct the signal pretty good. There are some samples missing in between, of course, but you can obviously see it's a sine wave, so this is a sufficient quality for your signal. Okay, so let's come to the next part, which is the data throughput and the storing. This depends, of course, on the sample rate, but also on the bus which is used. For example, PXI or PXI Express bus. For the PXI bus, you can reach data throughput up to 90 megabyte per second. And for the PXI Express bus, you can reach up to 400 megabyte per second. And within a system, when using multiple boards, you can use, or you can reach up to 1 gigabyte per second of data throughput. Also, the recording time has a lot to do with the data throughput or with the storing. So if we look at this example, if we record 100 channels with a sample rate of 1 megahertz and a resolution of 18 bits and a 24-bit word size, and we have a SSD with 1 terabyte, that comes up to a data throughput of 287 megabyte per second. And if we record this and store it on the SSD, we can record up to 1 hour until the SSD is full. So if we have high sample rates, the data throughput and the storing should be considered. I have another example here. So if we have a system with 500 channels and record 100 channels per system, we can I constructed the system here with our oxygen net option, where you can just connect all these systems very easily. They are synchronized by the train and sync bus, and with the oxygen net option, we also have the option of the data transfer and or the storing on the master device. So the configuration can also be done from the master device of all the slave systems. Speaking of remote control, you can just sit in front of the master device after setting up everything and then configure each system individually. So if we think, or if we say we have a sample rate of 500 kilohertz at each system, for each channel, and an 18-bit resolution, there comes up a data throughput of 144 megabytes per second per system. And we have a maximum recording time of 2 hours per system if we have an SSD of 1 terabyte. If we consider the data transfer to the master device, it comes up to 576 megabytes per second if we think we transfer all the data of all 4 systems to the one master device, which is possible with a 10 gigabit Ethernet. And if we also want to store all the data on each system and store all the data of each system on the master device, we can record 30 minutes on the master device until the SSD is full. So as you can see, if you have a large system, these are things which should be considered beforehand in order to avoid any problems afterwards. Okay, then let's come to the last part, which is the scaling and the bandwidth. So of course, the scaling is an important thing if the application is changing very often, if you need more or less channels for different applications, which is, as you could see in the example before, very easy with the oxygen net option, for example, or with other options that you can just connect the systems and measure more channels, or disconnect the system and have less channels for different applications. Of course, the bandwidth also has to be considered. For this, I have another small example. I have a rectangular signal sweep from 1 kilohertz to 30 kilohertz from the frequency generator and a sample rate of 20 kilohertz. I'll just open our software again and change the screen. As you can see here, we have the sweeps. I just freeze the screen, and as we could see before, if we have a sample rate of 20 kilohertz, we can reconstruct the signal up to a frequency of 2 kilohertz very good, and afterwards it will get smooth, and afterwards also the bandwidth has to be considered. So as you can see here in the beginning, we can see our rectangular signal, very good. And if we swipe or scroll through the recorded data, we can see the edges are smooth here, and it more and more looks like a sine wave since the edges are smooth, which might be an aspect which is very interesting for some applications maybe. But of course, if we scroll more and more, you can see it doesn't really have anything to do with our original signal anymore, and we cannot reconstruct it. Okay, so that was it for my part. Thank you very much. If you have any questions, just type them in the chat tool.
Yes, thank you, Verena. Actually, we do have a question, and you can decide if you want to answer it or if I should answer it. So we have one question. The question is as follows. I'm gonna just read it. How can I reach the best accuracy with the Trion module for 4-phase power analysis, and on what depends it most?
The accuracy?
Yes. So the accuracy of a 4-phase power analysis. I guess it's a three-phase AC and 1-phase DC. And what is the accuracy of the power analysis? What depends it most?
So For the power measurements, we have a known card, the Triumph power card, where there you can very easily set up a power measurement. You have direct current inputs and you can measure the voltage. For our card, we have a high accuracy, which goes from up to 1 kilohertz. So it's the same up to 1 kilohertz. And it of course depends on the sample rate. Like if you have a high sample rate, the accuracy is of course higher. And yeah.
Definitely. So
Okay.
regarding our measurement system, it's definitely the sampling rate, and it depends, of course, on the application, because not every power application is the same application. If you're measuring,
every application is different, so it also has, you also always have to look at the different application itself,
yeah.
and then see what's the best configuration you can get.
Yeah. Definitely, but two basics are sampling rate should be as high as possible. That's nothing you can do wrong for any kind of application. And one thing that doesn't match so much with our systems, but is very necessary, are the current transducers and current sensors. They have the most impact on power measurement and efficiency measurement, or on the accuracy itself. The delay of it, the phase shift error between voltage and current, which is a huge part if you measure the phi wrong. So I would always have a look at the sampling rate, of course, and definitely the current transducers. And if there has to be some kind of phase shift compensation, or how different those sensors are. So the current sensors are a pretty big part regarding power analysis, and that's the thing you should always have a look at. Yeah.
Yeah, and there's also the option to compensate a delay of the current transducers in the software. So, but of course, it's always limited to the accuracy of the current transducers itself. But that's from the sensor side then.
Perfect. Yes. Perfect. Yes. So that's the only question I see so far. I hope it was answered good enough. If not, please contact us directly. My contact data are on all the social media, and also on our webinar homepage. Our contact data are available there as well. Just a hint for next week's webinar. Next week's webinar is going to be about oxygen and the new features since 5.2 that we released, I guess, a couple of days ago or 1 week ago, something like this. For everybody who's interested, and for those who use oxygen, a very, very nice webinar to get you working easier and faster. A lot of changes have been made. That's from our side so far. Please follow us on social media for further informations. And if you still have unanswered questions, feel free to contact me and my colleague via email or phone. The contact data are available on social media or on our home pages. So that's it from our side. Thank you for listening, and I hope to see you next week again. Bye-bye.
Thank you. Bye.